morning, everyone. Good morning, everyone. Uh, Today we will continue from where we left off yesterday. So yesterday we talked about um, basics of algorithms, asymptotic notation, then ways to represent graphs in a data structure. Then we talked about one way to traverse graphs, right, which was depth first search. DFS. So what you basically do is you start from a vertex. It could be anywhere, and then just go to another vertex and another vertex, like and from there. So you go deep uh, uh, into unexplored vertices. So it's like you find a vertex that is not explored from, that is B, and then another one that is not explored, and another one that is not explored, and so on. And um, this is the depth first search approach. So you keep discovering new vertices and you keep exploring them, right? And what I've like this graph over here, the depth first search tree is consists. This is the entire thing is a depth first search tree, and there are two types of edges. One of them is the tree edge, and there are edges that are in the graph, but like for instance, you discover H, and when you're trying to explore the neighbors of H, you see that C is a neighbor, right? So this is what is called a back edge. So there are two kinds of edges that will encounter in the case of an undirected graph in depth first search. Yeah. And then we saw that the running time is O of V plus E, right? Provided the graph is given in an adjacency list format. If it was given as an adjacency matrix, then we would take O of V square time. Then we talked about, I think we talked about this. We wanted to identify which vertex belongs to which connected component, right? So we can use DFS for that. So what we do is this is the DFS code with some small modifications. So the blue things, the blue lines were not there in the earlier case. So now we have some new variables there's a new variable called CC, and there is a new array called CC_NUM. So CC is the index of the connected component, and CC_NUM is an array which has as many entries as the number of vertices. So at the end of the DFS, we will have this array filled up with which connected component each vertex belongs to, right? So I think we did this yesterday. So when you make, and we increment this counter CC whenever we make a call from outside, right? So if the entire graph is one connected component, then we will make only one such call. And therefore, the CC will just be incremented once, and the CC_NUM of all the vertices will be the same, because let's say the entire graph is connected. So from the first vertex that you pick itself, you will discover all the possible vertices of the graph. So there will only be one call of explore from the top level, and the rest is like recursive calls from within itself. But in the case of this graph, for instance, there are three connected components. So the way we said that we'll use alphabetical ordering to resolve types. So we'll first start and explore from A, which discovers this connected component. So A, B, E, I, and J have the number 1. And then you come back to the top level DFS, right? And then the first vertex that is not discovered in this array, in this ordering, is C. So you start a DFS from C, and then you discover D, H, G, L, and K. So those vertices have the index 2, right? And then you make just give me a second, I'll just silence my phone. Then you make one final call from F. Sorry. yeah, one final call from F, right? And that discovers just a singleton connected component F. So consequently, we have the index 3 for F, right? So this is very straightforward. There is no significant overhead in the running time. If I think it adds only an additional O of V running time, because all we are doing is filling up this additional array, right? Right. So this is a summary of what we did yesterday. So next, I want to talk about uh, something called pre-visit and post-visit ordering. I hope the screen is visible to everybody, since I'm using slightly different setup, and everything is very clear to like in terms of pictures, right?
Yes, it is visible.
Yeah, sure. Thanks. Okay. Yeah. Okay. Now I want to talk about this pre-visit and post-visit orderings. So this is the same graph, and this is the same DFS thing. So what we do is we are going to slightly modify the algorithm. So one is that we will have a clock which is initialized to 0 at the beginning in the top level, right? And this clock is incremented whenever we either discover a new vertex for the first time, or we complete an exploration from that vertex, right? So here I have filled up the pre-visit and post-visit entry. So I'll explain what it means, right? So we first started from A. We first started from A, right? So A has a pre-visit number of 1, right? Because maybe I should say initialized to 1. So yeah, I think then it works. Yeah, we first started with A. So A has a pre-visit number of 1, right? So we do two things. The pre-visit is done when a vertex is discovered for the first time, like when you call explore on that vertex. And once you explore all the vertices that are reachable, you exit from that call. At that time, the post visit is done. So both the times we increment the clock, right? So it may sound technical, but once we see the example, it will be clear. So the first vertex that is discovered is A, because we call the explore from it. So the pre-visit number is 1, right? The next vertex that is discovered is B. So the pre-visit number of B is 2, right? And then you see that from B there is nothing else to discover, right? Yeah, from B there is nothing else to discover. So you exit the call from B, the exit from B. So you complete the exploration from B. So you assign it a post-visit number of 3, because the last time it was 2, now you increment it, so it becomes 3, right? So the pre-visit and post-visit of numbers of B are completed. It is 2 and 3. Now you come back to A, but you're not done with A, because A has other undiscovered neighbors. So you see E. So E gets the next number for the pre-visit, which is 4. Then I gets the next number, which is 5. Then you discover J. And J gets the next number, that is 6. And from J, the only other edge that you see is E, which is already discovered. So there's no undiscovered neighbor of J. So you decide to exit the exploration or terminate the exploration from J. So you post-visit number is assigned 7. Now from I, there is nothing else to do. So post-visit of I is assigned, post-visit of E is assigned. Then you finally reach back A and see that everything that needed to be explored from there is already explored, right? So you assign a post-visit number to A and complete the exploration at A. So this component therefore gets these numbers, right? And the same thing gets repeated here. So C, so you get 11, then D, then you get 12, then you get H, so the H gets a pre-visit of 13, then G 14, then K 15. Then you realize that you have to exit, because all the neighbors are already discovered. So then you assign post-visit 16, post visit for G 17. Then you come back to H, then you discover a new vertex 18, 19. So then you exit H, so 20, exit D 21, and exit C then 22. Right. So now this thing is completed. For this component, the pre-visit and post-visit is completed. So now the only other component is the singleton component F. So the pre-visit is 23 and the post-visit is 24. So every time you visit a new vertex, the pre-visit is assigned. And every time you complete the exploration from that vertex, the post-visit is assigned. So whenever you assign one of them, you increment the counter so that the next time all the pre-visit and post-visit numbers of all the vertices are distinct numbers. Right? So there are 12 vertices here. So we go up to 24. Is it clear what these numbers are, the assignment process? Yeah, today if you're shy, you can respond in chat because in today's setup, I'm able to see the chat as well. Okay. Yeah. Is the process clear? Okay, fine. Okay, there are questions. Again, like I said yesterday, please feel free to interrupt me and ask questions. So this is the process. So now you may wonder what is the point of assigning these numbers, right? Like what? So these numbers are incredibly useful, and we'll see that they carry a lot of information. And like in the case of connected component, you also should realize that there is a very limited overhead in the whole thing. Like all you are doing is you are assigning a pre number and you are assigning a post number, and you have an additional variable called clock that you have to maintain, and a new or two arrays for called pre-visit and post, or pre and post numbers, right? You just have to maintain two arrays and do this operation. So the per vertex, you are just maybe adding constant time. So overall, you are probably adding O of V time for the entire process. So throughout the process still remains O of V plus E time, right? So the entire process, despite the addition of this, still remains asymptotically O of V plus E. All right. Okay, so now now that you understand the process, let's try to interpret these numbers, right? So first thing, is there anything interesting that you notice about the range pre-visit and post-visit? Right. So in a way, the pre-visit and post-visit is denoting the time window from which the explore call from that vertex is running. So the explore call from A runs from time 1 to time 10. Explore call from B runs from time 2 to time 3. Right? Then after the time 3, you exit. Explore call from E runs from time 4 to time 9. Right? So this is what the pre and post numbers indicate. So one question, so what are the possible relations between two of these windows, the pre and post? So if you have if you look at the the numbers pre, or the interval pre V to post V for each vertex, and if you compare the numbers for two different vertices, what are the possible ways in which we can get them? Okay, what I want to say is that if you look at the pre and post numbers of two vertices, what are the possible ways in which these intervals can relate to each other? So in the case of A and E, the window for E is completely contained inside A. In the case of, let's say, A and C, the window for A is disjoint from that of C. In the case of, let's say, I and H, 5, 8, and 13, 20, they're disjoint. So what can we, so in general, what is the observation that one can make? So what I want to say is that in general, there are only two types of relations, or maybe three types of relation possible between the windows of two vertices, let's say U and V, right? Either the interval of U is contained in the interval for V. Yeah, somebody has responded. That's correct. Or the interval for either the interval of U is contained in the interval of V, or the interval of V is contained in the interval of U, or they are entirely disjoint. So we will not have the situation where the interval for U is like this and interval for V is like this. Like they are neither contained nor disjoint. They intersect in some middle place. This cannot happen. The reason, so yeah, so this is what I've written here. For any two vertices U and V, either if you look at these intervals, they're either disjoint or one is completely contained inside the other. And the reason is uh, either U is called explored as a U is discovered when V is being explored. In which case, the interval for U will be entirely contained in interval for V, or V is discovered when U is disjoint. V is discovered when you explore from U. In which case, the interval for V is contained inside the interval for U, or you don't discover either one from the other. So, which means they are in different connected components. In which case, the exploration windows will be disjoint. Right. So this is the same thing that I'm saying. Either explore V is called as a descendant of explore U, in which case this V, the interval for V will be contained, or it is called after explore U is completed, in which case it will be disjoint. Right. Another way to, like, if you understand the concept of recursion in a computer science way, like recursion is like when you make recursive calls, you have a state of the algorithm, and this state is stored in a what is called as a data structure called stack, right? So when if V is called as a descendant of U, then we can say that V when explore V is called when U is still in the recursion stack, right? So that's what I'm trying to say. Yeah. So otherwise, it's they're disjoint. Okay. So that's about it for the relations, and we'll see more interesting things about these numbers, and we will make use of them for deriving properties about directed graphs. So far we have seen undirected graphs. In undirected graph, the DFS tree has basically, or the DFS results in two types of edges, either tree edges or these back edges. But in directed graphs, we'll get way more types of edges. Okay. So let us try to run the algorithm, depth first algorithm for this graph. Right? So you start from A, right? Then you see B is an out neighbor, so you go to B. So you can also follow the pre number 1 and 2 for A and B respectively. And from B you see E. So you come here. So you have assigned a pre number of 3. Now from E you see F and G. So F is alphabetically earlier. So you go to F. Okay, you also have H here. Sorry, H here. But F is alphabetically first, so you come to F. From F, you go to G, right? So this is the main thing about depth first search. So even though you know there are other neighbors for E, you don't explore them till you complete the exploration from F. Right? So you go completely deep before exploring other things. So from F, you discover G, and from G there is no out neighbor, so you go back to F. So now the exploration from G is complete. So the post number is assigned. From F, there is no out neighbor. The only other out neighbor is B, which is already discovered. So you exit from F. So post number is identified. Then you come back to E. Then there is an undiscovered out neighbor, H. And from which nothing else is there to be discovered. G is already discovered. So pre number, post number, both are assigned from H. Then you come back to E. Nothing else to explore. Go back to B. Nothing else to explore. You go back to A. So all for this subtree, all the pre and post numbers are assigned. Then you see that there is a new unexplored out neighbor C. Then there is a new unexplored out neighbor D. And then you see that like from D, you can see H, but H is already discovered. So you go back to C, you go back to A, and then you are done. So similar, like consequently, these numbers are also assigned. Right. So this is DFS process. Just that now we have to be careful about just out neighbors, but not we don't explore through in neighbors. Right. So from A, you don't go this way because the edge goes the opposite way. Right. From H, we did not discover D because this was not an out neighbor. Right. So now in this case, earlier we had two types of edges: the tree edges and the back edges. In the case of undirected graph, right? In the case of directed graphs, since directions are involved, so the red edges here are the tree edges. The other edges, the non-tree edges, are generally of three types, right? One is that so the back edges can have like whatever were earlier back edges now can have two directions. So earlier we indicated them by dotted lines and called them back edges. So now they could be either pointing this way, in which case we call them back edges. So back edges are the edges from descendant to an ancestor. Then, or the back edges could be pointing this way, or which is now no longer called back edges because now they are from ancestor to descendant, but not the tree edges. So ancestor to non-child descendant, right? So it could be grandchild or great grandchild or something. So these things are called forward edges, right? So this is like the back edges that we saw earlier now could be either like back edges or forward edges, right? So back edges means descendant to ancestor, forward edges means ancestor to non-child descendant. Then you have a new type of thing which was not there earlier, which is let's say like this, like from H to G, right? This is an edge of the graph. Can you tell me why it was not there earlier? So this is H to G is neither a back edge, it's neither from ancestor to descendant nor from descendant to ancestor. It's going from like some vertex to some other vertex. Why was it not there for the undirected case? Why didn't we have it for the undirected case? Anyone? Or is it that we just that in our examples it did not show up? Can we have it for the undirected case? Somebody please respond. We would have already visited in the case of an undirected graph. So let's try to understand. So suppose this was an actual edge and we were in the undirected case. So in this particular, like between H and G, in the undirected case, if this was an edge, right? So now the problem is that H cannot be discovered from G because the edge goes the opposite direction, right? So if it was undirected, then we would have had so H was not discovered at this point when you're exploring G. In the undirected case, H would have featured as a child of G, right? We would have discovered H from G. So it would be a child. So the reason this happens is because there is a vertex that that you cannot discover because the edge is pointing the wrong way. So that is why this happens. And all the so this is called cross edges, right? So G is Rahul is saying G is neighbor of H, but not vice versa. Yeah. Just to be clear, G is out neighbor of H, but H is not out neighbor of G. Right? Yeah. So the cross edges. So we call them cross edges, and this happens when you this comes from a vertex that is later discovered to a vertex that is earlier discovered. So that's the type of edges. So we'll not have a cross edge going this way, like from a vertex that is earlier discovered to a vertex that is later discovered, because then we could discover that vertex as part of the depth first search itself, right? So the three types of edges that are not the three edges. So all of them I have shown with this pencil type of thing. Right? So the forward edges are in this picture are A to F, E to G, and that's it. The back edges are D to A and F to G. And there are two cross edges, H to G and D to H. Okay. Okay, so now I want to say some things about these edges. Right. So let's see what are the relations between pre and post numbers when for each type of these edges. There are four types of edges that we talked about, right? So if it's a tree edge, or if it's a forward edge, if it's a forward edge, let's say this one, UV is a forward edge. So this is U and this is, let's say this is V. Then you have first pre-U, then pre-V, then post-V, then post-U. So for edge UV, if it's a forward edge, then pre-U, pre-V, post-V, and post-U, right? So this is the case even if it's a tree edge, right? Even here, that's the case. Maybe I'll just add it here. Or tree edge, if these relations are true. Right. So you can see that this is the case for all the tree edges and all the forward edges. What is the relation for the back edges? It is opposite. So this is the UV, let's say the edge UV. So you have pre-V, pre-U, post-U, and post-V. Right? So back edge, if these relations are true, so here forward edge, here tree edge. Back edge means it's flipped. Basically, the U and V change the roles here. And in the case of cross edge, let's see what happens. In the case of cross edge, let's say this is UV. So you have pre-V and post-V, followed by pre-U and post-U. So they're disjoint, and U comes after V, right? So cross edge, if we complete the exploration at V, so pre-V is less than post-V, and then you complete the exploration at U. So pre-V, post-V, pre-U, post-U. Clear? So forward edge and tree edge, it's case 1, back edge, it's case 2, and cross edge, it's case 3. Is it clear? Any questions on this? Okay, if you have questions, please stop me and ask. So one thing to note here is that whenever you have an edge UV, in the case 1, forward edge or tree edge, in the case 1, you have post U coming after post V. Case 3, the cross edge also post U coming after post V, meaning coming not immediately after, but it post U is greater than post V. Only in the case of back edge do I have post V greater than post U. Correct? Yeah. So this will be using it soon. So back edge can be distinct. So how do we identify a back edge? So you do DFS and you check if for a particular edge we have post V greater than post U. Then the edge UV is a back edge. Right. Okay. So now I want to talk about finding if a given graph or a directed graph has a cycle. Okay. So the claim is that a directed graph has a cycle if and only if the DFS tree has a package. Can somebody explain why this is the case? I've written something. So directed graph G has a cycle if and only if the DFS tree has a package. I think this is true for undirected graphs also. They're also the same thing. Somebody can at least explain one direction of the proof. Suppose there is a package, then can we say that it indeed has a cycle? This picture may help. I think you can unmute and explain if you like to explain. Suppose there is a package, how can we say that there is a cycle? Everyone knows what a cycle is, right? Okay, maybe I'll explain since yeah, if something is unclear, please respond. Okay, please ask questions. So suppose there is a package, it's a UV. So here it's from F to B. Package means it is from a descendant to an ancestor, right? So there is already a path from the ancestor to the descendant, right? Using the tree edges. So now this path using the tree edges together with the package going back to the ancestor completes a cycle. That's about it. So if there is a package, the path from the descendant, the path from the ancestor to the descendant, plus the return path back to the ancestor completes a tree. So UV is a package, which means there is a path from V to U in the tree. Then you add the edge UV, that completes the cycle. Now, what about the other direction? Okay, there is somebody who's written something. DFS goes in the direction towards depth. If it has package, it forms a cycle. Yeah, so thanks. Excellent. Right. Right. If it has let's say A to B in DFS, then B to somewhere, let's say X has a package, then I think it's a bit simpler than what you have written. It's if A to B, if it has a package, let's say from, I don't know what you mean here. Okay, so the point is very simple. If there is a package U to B, then that together with the V to U path, because package is from descendant to ancestor, then there is also a path from ancestor to descendant. This package combined with this path forms a cycle. Right? So even here, BA is a package that together with the AD path forms a cycle. That's pretty much it. Now the opposite direction. So remember that it is an if and only if statement. Package if it exists if and only if G has a cycle. So now we showed that if package exists, the G has a cycle. How do we say the opposite? If G has a cycle, package if G has a cycle, then package certainly exists. Right? So we want to say the opposite direction. So it's an if and only if statement. So both ways it's true. So if G has a cycle, how do we say that it necessarily must have a package? Any ideas? if G has a cycle, what can we say how the, let's say it has, let's say some 10 vertices in the cycle. How are they going to be discovered? Will all of them be explored at the together or in separate components? They will not be discovered in separate things. It will all be discovered together, right? Okay, so Rahul is saying if we reach any vertex of the cycle after exploring the package will be there. Yeah, that's pretty much the idea. So there is a cycle. Now, at some point, a vertex is going to be discovered, right? So let's say the V is the first vertex that is going to be discovered in the cycle, right? So let's say V is the vertex that is going to be discovered first in the cycle. Let's say called V as part of the depth first search. Now, the point is that all the other vertices of the cycle like will feature as descendants of V, because from V, we could have other neighbors, not just the vertices in the cycle. But before we exit the exploration from V, you will certainly discover the next neighbor and the next neighbor. And all of these vertices in the cycle will show up in the DFS tree as descendants of V. Maybe immediate children, maybe not, but they will, all of them will be in the subtree of V in the DFS tree. Okay, so now in the cycle there is a preceding vertex of V in the cycle. The preceding vertex, let's call it U. So which means U is in the subtree of V, and the edge UV will be a back edge. So look at the first vertex that is discovered, that is V, and all the rest of the vertices in the cycle will be discovered as still descendants of V, and so UV will be certainly a back edge of the tree. So back edge, if and only if there is a cycle, right? So now you want to know whether a certain graph has a cycle. Then how will you do it? How will you find out if a directed graph has a cycle? If you have to come up with an algorithm. Excuse me, Rajesh. Rajesh, there is
Yes,
somebody in
yes.
the waiting room. Should I just admit people as and when I see them?
You can admit. I'm also admitting from here.
Okay, sure.
Yeah, yeah.
Yeah, thanks. Uh, okay, so now suppose we want to identify if G has a cycle. How can we do this kind of very efficiently, very quickly using the DFS? So I've already kind of told you the answer, but you just have to repeat it.
So is post U less than post V?
Yeah,
Like
basically we have to check if there is a back edge, and back edge is the only type of edge where you have this property, right? So back edge is the only one which has this property. So you just check, is there any edge in the graph that has this property? And if it is there, then it has a back edge. And if it has a back edge, there must be a cycle. And if it has no back edge, then there is no cycle. So you understand this if and only if relation is essential for us to make this inference. So we are claiming that both ways. Okay. So if you want to determine if the given directed graph has a cycle, then you just look at the post numbers. Right? So this I think I already said this. So if UV is a tree edge, forward edge, or cross edge, then post U is less than post V. If it's a back edge, then post U is, I'm sorry. If UV is a tree edge, forward edge, or cross edge, then post V is less than post U. And the only case where post U is less than post V is if it is a back edge. So to check if a directed graph has a cycle, you can just do DFS on it and then check if there is an edge UV, right? If there is an edge UV with post U less than post V. That's pretty much what you can do. Okay, so that is about that. So now I want to move into something more interesting. Any questions so far? Okay, I want to talk about something called topological sort. So what is topological sort? So if you have a directed graph without cycles, so I call it directed acyclic graph, a directed graph without cycles. The question is, can we order it in such a way? Can we order the vertices in such a way? Meaning you want to lean like in a let's say you want to order them in some ordering, so that all the edges of the graph go from vertices that appear earlier in the ordering to vertices that appear later in the ordering, right? So first of all, can this be done itself is not very clear. So for instance, I don't know, in this graph, is there a way to do it? So can you do this in this graph, for instance? Is there a way to order the vertices so that all the edges, let's say A, B, C, D, E, F, G, H, the alphabetical ordering, are all the edges from the vertices appearing earlier in the ordering to vertices appearing later in the ordering? So A to B is fine, A to C, A to F is fine, B to E is fine, but D to A is there, which is an edge that is going in the not in the alphabetical ordering, right? So alphabetical ordering doesn't work. But is there any ordering in this graph which satisfies the property, which satisfies the requirement rather? Is my question clear?
Not really. The question is not really clear.
So let's consider okay, thanks. I'll repeat it. Yeah, please respond when I ask such things. Only then do I like I'll be able to know if I'm like if people are following or not. So we want an ordering such that, so let's consider the ordering maybe A B C D E F G H here. Right? Maybe I'll just write it somewhere. Maybe I'll just write it. Right. So let's consider this ordering A B C D E F G H. A, B, C, D. I'm just writing the above graph in a different way. Okay. Now there is an edge from A to B. There is an edge from A to C. There is an edge from A to F. Right. There is an edge from B to E. There is an edge from E to F. So all of these edges that I'm writing are going from left to right. Okay. There is an edge from E to G. There is an edge from F to G. There's an edge from E to H. There is an edge from C to D. There is an edge from D to H. So all the edges that I've drawn so far go from left to right. But however, this edge is there, H to G, which is not going in that way. There is also this edge, right, that is going in the opposite way. I think I've drawn all the edges. No, there is also one more edge, F to B, which is also going the opposite way. So the question is, so alphabetical ordering doesn't work. The question is there an ordering of the vertices of this graph so that all the edges go from left to right? So this ordering doesn't work, right? There are three edges, at least three edges. I think we have covered all the edges. At least three edges that go from right to left. Now, my question to you is there any ordering of this graph? So maybe this ordering doesn't work, but maybe some other
No,
ordering.
probably not, because there is a cycle. So if back edges exist, so it's not possible to have that ordering.
precisely. So it is not possible for this graph. It's not possible because, so maybe I'll use another color. So no, it is not possible for this graph. For this graph, since it contains a cycle. Since it contains a cycle. So whichever way you order the cycle, like basically you cannot keep going right and complete a cycle, right? At some point you have to complete the cycle, so you'll have to come back to the left, right? So like a cycle, you cannot do a cycle by keep doing this, it'll not get a cycle. So you need some edge that comes back, right? So we will need some edge that goes from right to left. So if the graph does not has a cycle, then certainly it's not possible. Is there a way to so in this graph? I think this just as a side comment, this basically this edge we can get rid of. We can if we put G after H, then this will become a forward, like in this ordering, it will not be like something that comes from right to left. But the other things are kind of unavoidable because I think DA is part of a cycle. ACD is part of a cycle. So even if you try to move something around, there will certainly be a back, something from right to left. Okay. So anyways, so that's fine. So the question is, in this graph, it's not possible to order the vertices so that all the edges go from left to right because it contains a cycle. Now, another question is, now, is it possible? So if you have a cycle, it's certainly not possible. What if a given graph G does not have a cycle? Right? So suppose G does not have a cycle. In such case, is it always possible? Right? Now you get the question. This is what I mean. Is the question clear?
Yes, sir.
Yeah. So this ordering is called, maybe I'll write it here. Such an ordering is called topological sort. Does it necessarily, does G necessarily have a topological maybe this is topological sort. So if it has a cycle, it cannot have such an ordering. The question is, if it does not have a so lack of having or not having a cycle is a necessary condition. Is that sufficient is the question. And the answer is that it is sufficient. So suppose I have a graph that does not have a cycle, then it must necessarily then it necessarily must have such an ordering. Right? So the statement itself is somewhat it may not be immediate, like how can we say this, right? The statement itself requires some thinking or some proof. So the way we will do it is we will show it is by giving a constructive process by which an algorithm by which we can construct such an ordering. So given a directed acyclic graph or given a directed graph without cycle, we will show how to construct such an ordering. So the only condition we need is the lack of a cycle. And this is also based on depth first search. And we'll use all these things that we have built up so far. The same graph or is it different graph? So ACD is a cycle here, and BEF is a cycle in the original graph. So I think in this picture, so yeah, so basically what they have done, I took this example from somewhere. So basically what we have done is that in the earlier, basically we had two back edges. Now we have removed both of them. Right. So now this is a directed graph without cycles. Right. Now we want to find out a topological ordering. How will we do that? So we can do DFS and we get these DFS tree with these pre and post numbers. Right, it's the same as before. Right. Now we see that we have tree edges, we have forward edges, and we have cross edges. There are absolutely no back edges because there are no cycles. Right. Now, can you tell me, with whatever we have learned so far, there is something that we have learned already. What would give us such ordering? So we said this. So forward edge and tree edge have this relation. Back edge has this relation. Cross edge has this relation. So now, for all the edges that are in the graph and these numbers, we have post U, all the edges UV, we have post U greater than post V, because here also it's the case and here also it's the case. So for all the edges in the graph, I have post U greater than post V. Now, how do we use that to build an ordering like that? So we already know the answer, we just have to think and retrieve it from whatever we know. So for all the edges we know, let's say we consider this edge, post number is 16 and 11. And this edge 16 and 7. So for all the edges, the post number of the UV, the post number of U is greater than post number of V. So now, given these numbers, how do we construct that such ordering? Somebody should know the answer. It's not that difficult. It's okay if it's slightly incorrect or something. Please at least attempt. Do DFS starting from each elements and see where it is proper tree. No, we don't have. So what I'm saying is all we need is already here in this picture. So you do DFS from anywhere and you get all these numbers. And I'm claiming that already here there is enough ingredients to form the ordering.
I mean, isn't the alphabetic ordering already that's the same ordering? Yes.
Let me see.
Right.
A, B, C. Yeah, in this case, the alphabetical ordering works, but that's just because we assign labels this way. Yeah, in this case, the alphabetical ordering does work. But I want, like, if I had like jumbled up the letters A, B, C in some other way, then it won't work. But I want an answer which is instead of the names here,
Generalized,
using the DFS things. We have already seen this. So how can we make use of this? Sorry, how can we make use of this property? For all the edges in a directed acyclic graph, so DAG stands for directed acyclic graph, we have post V is less than post U. So for all the edges, so look at this picture here. A to B, A has 16 post number, B has 11 post number. C to D, 15 and 14. D to H, 14 and
Okay,
9.
if I do it like descending order of the post,
Correct.
like
So
this.
you can just sort, you can just order the vertices in the descending order of post numbers. And it must be the case that now all the edges are going from earlier in the ordering to later in the ordering. So yeah, so that's about it. So I think if you do that, then A comes first because 16, then C 15, D 14. Right? I've written it at the bottom of the screen. Then B, E, H, F, and G. And you can see that all the edges go from right to left. Sorry, left to right. This is, as you already noted, this is not the only such ordering. In fact, the alphabetical doesn't work, sorry, because there is an edge from H to G. So alphabetical doesn't work. So yeah, but there are other things you can do. So bringing B in front of C doesn't really, it still retains that property. So this is not the unique such ordering, but one such ordering can be recovered by doing DFS and sorting the vertices in the descending order of post numbers. Okay. Yeah. Yeah. So yeah, take somebody else has answered. Yeah. Yeah. Okay. So this is about topological sort. So this is something that has that you can imagine have applications. Let's say you have to schedule jobs or something, and each like the some jobs may have some dependencies. Like you can only do certain jobs after like some information. Let's say processes in computers. You can only do certain processes after some previous processes are complete because you need the output of that. To execute this process, or it could even be a manufacturing cycle or something. There are different things. Let's say manufacturing a car, different things are being manufactured. Some of these things can go in parallel, but then you need certain things to be complete before you can, let's say, certain assembling can happen, right? So as an assembling can happen at various stages. Maybe assembling, let's say, gearbox can happen, maybe assembling the entire thing can happen. So you would want to figure out an ordering of these jobs so that you don't want to start or attempt to start a job, then realize the input to this job is not there. So it's important to have an ordering of these jobs so that whenever you start a job, whatever necessary things to complete the job or execute the job is already there. Another example is, let's say you are in a some student is doing a degree and he has to complete, let's say, many courses as part of it. But then some courses, let's say, some courses, for instance, require some other courses. Let's say algorithms requires discrete mathematics as a prerequisite. So you don't want to do it in the opposite way. So you want to find out an ordering of courses so that you do all the courses in, and whenever you are doing a course, you have completed the prereqs. Right? So this is also another example. So it's something that's very useful, and it's also nice to know that not having a cycle is also a necessary and a sufficient condition. Okay. And I also, as I already said, this thing need not be unique. The ordering need not be unique, but we need one such order. The next thing I want to talk about is strongly connected components. Okay. Any questions so far? Okay, if you have questions, please ask. So now the thing is, we want to generalize the notion of connected components to directed graphs. Okay, so you have connected components where, like, what are the vertices reachable from a certain vertex? We saw this example of in undirected graph where we had connected components, right? Now so here there are three components, three connected components, right? This one, and F is a single term. Now, what is a reasonable generalization of this? So this, in the case of directed graphs, it's not that straightforward because sometimes you can go from one vertex to another, but then you cannot return back. So it's like, even though if you look at the thing, everything may be connected. So here in this graph, everything is connected, but then there is no way to go from, let's say, H to F, for instance, right? Is there a way? Oh, there is a way. No, there is no way. You can go from H to G, but then there's nothing to do from G. So the generalization, or one generalization that works, is called strongly connected, and this is a notion specific to directed graphs, right? So we say that a subset S is strongly connected, okay, if a subset S of vertices is strongly connected, if for any two vertices U and V, there is a path from U to V and there is a path from V to U. Okay, so we say that a subset is strongly connected if for any pair of vertices U and V, there are paths both ways, from V to U and U to V, right? So now let's try to identify, maybe you can try to identify the strongly connected components here. What are the strongly connected components? Here. Are there any strongly connected components? Not sure. No, this does not have strongly connected components because it's a directed acyclic graph. Yeah, so it doesn't, because U to V and V to U forms a cycle. So this does not have strongly connected components. Let's take this graph and we want to identify the strongly connected components. Can you tell me which are the strongly connected components? Yeah, this is the graph. Tell me any one.
BFC,
Yeah, please go ahead.
BFC, though two
B,
components,
B and
BE
huh.
and
B,
CF.
BE is BECF, all of them together?
No, not together. Two components.
Right. So BE is a strongly connected component and CF is a strongly connected component. And notice that you cannot add anything and you cannot expand this strongly connected component because like all four of them, for instance, you cannot make one strongly connected component because there is no way to go from C to B. There is no path in this graph that will take you from C to B. So BE is one. What about A and something else? Is A, what is the strongly connected component that is?
Not possible for A because there is no in neighbor.
So A is a strongly connected component individually, right? Because trivially there's only one vertex, so you can say that D is also one such component because from A there is nothing coming to A, so you cannot put A with another vertex because if you put A with another vertex, let's say X, there is no path from X to A, and similarly from D you cannot go to any other path. So right. And what about the rest of the vertices? G, H, I, J, K, L.
IJG.
I, J, G. Is this a strongly connected component? Yeah, you have paths from one to everything, but is this the best we can do? So this is a strongly connected component as per what I defined, but I want to find out the biggest possible such components. Like, of course, I can just say that all of them are strongly connected components by itself because they are singleton vertices. But I want to find out, can we somehow bring more into this?
We can add HK and L to IJG.
Yeah, so basically this entire thing, if you take, this is a strongly connected component because you can go from any vertex to any vertex. So G to H, there is a line, there is an edge. H to G also you can find out now. H to G you can come this way. right? So basically there is a cycle like this. So you can go from any vertex to any vertex in this, right? So this is the best way in which we can divide into strongly connected components. Best meaning I found out the largest possible such components. You know, no such component can expand. So we can draw a metagraph of these strongly connected components. What I mean by this is that let me see. So what I want to say is this. Let's say I can draw a graph with these components as vertices. B comma E. So by B comma E, I'm talking about these components. C comma F. Then G H I J K L, and then we have B, right? And now what are the relations between these strongly connected components? So there is an edge from A to B, so I will put an edge from A to this component. There is an edge from B to C, there is an edge from E to F, so I can put an edge from here. The edge from B to, so edge from here. There is an edge from E to here. Is there any connections that I have missed? Anything that is going across, like inside the component, I don't have to do anything. But anything that goes across B to C, E to F, E to G, and F to H. Right. So this is what I mean by a metagraph. So a metagraph of the strongly connected components. Yeah. So Vishnu Hemant says that it is a DAG. I agree, it's a DAG. Why is it a DAG? So it's certainly a directed graph. So why it doesn't not have a cycle is the question. So this metagraph is a DAG, is a claim, meaning it is acyclic. So why can't we have, let's say, an edge like this? If it had an edge, then what could it have claimed? Or an edge like this, or like this. Why is this necessarily acyclic is the question. Cycles are subsumed in the nodes of the metagraph. Yeah. So so you can say that. So basically the thing is that if there was so if you take B and E here, there is a path from B to E and there's a path from E to B. Now, if there is an edge like this, if it was cyclic, which this would form a cycle, or if there is an edge like this, then from A you can go to B, and from B you could go to A. So A and B, so you could make a bigger strongly connected component containing all of this. So this is what I say here. Okay, I don't say here. Okay, maybe I want to say so this, maybe I'll say it now. This metagraph consisting of SCCs as vertices and with an edge from, let's say, SCC C1 or Ci to SCC Cj if and only if there exists U in Ci and V in Cj such that UV is an edge of G. This graph, this metagraph is necessarily acyclic. Right? So this graph is necessarily acyclic. Now the question is, given I think I said this somewhere. Okay, maybe I'll come to this. So now one more point. If you have a DAG, I can also say some basic things. So in a DAG, we don't have cycles, right? And I will say that let's say this vertex in a DAG, this is a source vertex, meaning this is a source vertex, meaning it does not have incoming edges, right? D is a sink vertex because it does not have outgoing edges. It only has incoming edges. So this is neither a source or nor sink. This is neither source nor sink. This is a sink vertex, right? So I just want to use that terminology also. And whenever you have a DAG, you can, or whenever you have a directed graph, you may have source and sink vertices. Even here, I think A is a source vertex. F is neither, B is neither, G is a sink vertex, H is neither. Yeah, basically A is a source, A is the only source, and I think G is the only sink here. Yeah, yeah, so this is something I want to just say. So maybe I'll write here is where to write. Maybe I'll write here. This is a source. No incoming edges. So for any DAG, we can say this. Or for any directed graph, I can define source and sink. These two are sinks. No outgoing. Just okay. There's a question. Is and we have more than one metagraph corresponding to a directed graph? Can we have, okay, so the question is, can we have more than one metagraph corresponding to a directed graph? No, not really, because basically what I mean by the metagraph is you take the largest such connected component, strongly connected component. So there is only one such collection. Like if for every vertex I pick the largest such strongly connected component that it belongs to, right? So maybe I should say this maximal. Maybe I say this word here. Maximal strongly correct. Maximal meaning the largest such thing, so you cannot add anything more. In this case, there is only one such thing. You cannot add any vertex to any such thing. And that is what makes it, being maximal is what makes it a DAG. For instance, if this SEC was split into two parts, let's say GH and maybe something else, then it will not be a DAG, because the resulting metagraph will have edges going out as well as in, and you can form a cycle in that. There will necessarily be a cycle in that. So by this metagraph, I want it to be acyclic, and which means all the components should be the maximal such components. Is it clear? Have I answered the question?
Yes.
Sure. Okay, so now the remaining thing that I want to do is maybe I'll do complete. That's the last thing I want to do about DFS. Given a directed acyclic graph, I want to use DFS to recover this structure. I want to first identify the strongly connected components of the graph, and then I want to use DFS to also identify which strongly connected component each vertex belongs to. So kind of like earlier undirected case where we identified which which connected component each vertex belongs to, but now I want to use it for strongly connected components. Right? So how will we do that is the question. Right? So the goal is clear, right? So given a directed acyclic graph, I want to come up with this this structure. Basically, this structure meaning I want to identify the strongly connected components, and for each vertex, which connected component does it belong to, or who are my partners in the connected component, right? So again, this can be done using DFS, and this again, even this can be done in O of B plus C time. Right? Okay, so let's try to understand how to do this. Can you tell me if you have to do some exploration and find out just one strongly connected component, but the full component, right? How will you do this? Suppose you have to recover one strongly connected component. So if you explore from A, so let maybe I'll
I mean,
rephrase.
find a back edge with the highest range between the 3 values or something like that.
Not really. That's not the answer I'm looking for. So suppose maybe I'll just ask it in a different way. Suppose I start and explore from A. I think you end up discovering the entire graph, right? All the vertices will be explored. Suppose you start and explore from B, then you discover everything but A. If you start explore from C, you discover what all do you discover? You start and explore from C, which are the edges, which are the vertices that you will discover?
F.
F, only F or something else also?
Then again H and go
Then
on like
once you
that.
find H, then you find K, then you find L.
Then the entire thing.
Basically, if you start and explore from C, you discover both of this. If you start from B, then you discover this entire thing. Why is this happening? Or what is the logic here? In terms of the metagraph, can this be explained somehow? So basically, what is happening is that if you start a explore from, let's say, F, you will discover everything in its strongly connected component and everything that are reachable from this also, right? So you will discover these two things if you start a explore from F or C. If you start from B or E, then you will discover this, and so this entire thing. What happens if you start explore from D?
Nothing.
Basically, you just explore only that.
D.
So now, if you start and explore from, let's say, G, what happens? Or let's say K, then what happens? You recover this entire strongly connected component, right? So what I'm trying to say is that if you start explore from certain vertices, then you recover only that strongly connected component. So which are these vertices? Is my question clear? So if you start explore from A, then you recover everything. But which are the vertices from which if you start explore, you only get those vertices that are part of a single strongly connected component?
Okay, the sink.
Correct. So the point I want to say is that if you start and explore from a sink strongly connected component, so there are two such things here. There is this SEC which contains only D. There is this SEC which contains G, H, I, J, K, L. Then you end up finding that entire strongly connected component. So if you start and explore from L, you discover this entire thing. G, H, I, whatever. Anything that you pick from here, you discover this entire strongly connected component. If you start and explore from D, you recover only D and nothing else. So what I'm trying to say is that if you start the explore from a sink strongly connected component, then you discover only which does not have an outgoing edge, which meaning the component should not have an outgoing edge, right? Not the like individual vertices may have, but only to the same component. Right. So the question is, how do we now suppose the goal was to identify the component. I can do it by just starting the explore from a sink strongly connected component. But the question is now, how do I identify a sink? Like how do I get a sink? So maybe let's do this thing. Let's try to do some let's try to yeah, so I think the answer that this is what I will be discussing. If we start explore from a vertex in a sink strongly connected component, then we will terminate once we explore the entire strongly connected component which contains Q. And the question then is, but how do we get such a vertex? So now maybe we'll just quickly do this. We'll try to label these vertices with the pre and post numbers. Let's say we start from A. So 1, and then you discover 2, or B, which is 2. Then you discover C, which is 3. Then you discover F, which is 4. Then you discover H, which is 5. K, which is 6. L, which is 7. J, which is 8. I, which is 9. G, which is 10. H is already discovered, so you have to retreat. Exit G, exit I, exit J, exit L, exit K, exit H. There is nothing else you can see from H, so you come back to F. Is there anything else that you can see from F? No, so you exit F. Is there anything else you can see from C? Okay, from F you could see C, but that's also done. So from C you cannot see anything else, so you exit C. From B, what else do you see? You see D, so you explore D, 19. Then you exit D because nothing else, 20. Then you discover E, which is 21. But then all the neighbors are identified, so 22, 23, 24. Right? Okay, so we did this thing. The question is, how do we, in this entire graph, do these numbers tell anything about sink strongly connected component? It's not that clear because D is a sink and it has 19 and 20 as numbers. 19 is neither the earliest nor the latest, nor is 20. Over here also you cannot say that. Do we have anything that discovers the source vertices, source strongly connected components? Do we have anything that kind of discovers a source strongly connected component? There's only one source here, so it's hard to. And we happen to pick that as my starting point. But we need not have picked A as a starting point. Okay, since maybe I'll is it okay to like go for another 5 to 10 minutes and complete this thing?
The next session is at 2 o'clock, Subru. So you have to go for
Oh, I
lunch.
see. Okay. So maybe I'll just stop in a minute or two, and then we'll anyway in my next in my afternoon session I will complete this and before we go to the next topic.
Sure, sure.
Okay, thanks. So fine. So what I will do, so the point I want to say is this. there is no way to discern these sync strongly connected components from these numbers, but there is a way to discern the source strongly connected component. The vertex with the highest post number will necessarily be a source, will necessarily be part of the source SCC. Okay. Okay. So this we already saw. If we start explore from a vertex in a sync, then we'll terminate once the entire SCC is completed. But this is a statement that I just said. The vertex with the highest post number must necessarily be in a source SCC. Okay. So maybe what you can do, since it's next session is at 2, I don't want to run over time. I'll just stop now. Just think about this and why this is the case. Yeah, I think I'll stop now. Rajesh, I will once I complete, I will share the notes with you again, because since we have added some things, if you're not already shared, or if you've shared already, you may have to reshare with the participants.
Okay. Yeah. Yesterday, whatever you gave, I shared with them. Maybe again.
Oh, but then I think I'm just for the like if everybody's attention, I'm just saying that I'll reshare it because we wrote some things and there is more annotation. So I'll update this, and maybe today after we complete, I will share it. Yeah. Okay. I think I will just stop it. There is not much left in this topic. So after this, I will talk about breadth first search in the afternoon. Yeah. Okay. So thanks. I'll stop now.